Hi, in this video I'm going to review brain function and childhood development. So in the developmental course, we're going to go over all the different mechanisms that are involved with dysfunction in child development. So what I want to do in this video is just kind of get you caught up with some of the basic neuroanatomy and different structures that are involved with normal brain development. Because I know a lot of people don't have a lot of background or remember many things associated with neurological pathways. So let's start with the very basics. One of the things that is really important to know is which neurological pathways are developed at birth. So you need to know that the brain doesn't completely develop till about age 18, 20, 21. So we have this developmental phase that's happening during fetal development. Then we have a period of significant growth the first 2 years of life. And then we have gray matter that starts to fully develop by age 10. And then white matter continues to develop all the way to around age 18, 19, 20, and 21. So the brain is constantly developing throughout childhood and late teens and early adulthood. But when the child is first born, there are certain pathways that are already intact and they're ready to help develop other areas of the brain, and there's pathways that are necessary for just normal function, and there's reflexes that develop in the spinal cord that are involved with survival functions. So let's start with this diagram here. And the first thing to know is that visual pathways, auditory pathways, and vestibular pathways are developed already at birth, right? So over time, motor development takes place, sensory development takes place, auditory development takes place, intellect takes place, and cognitive functions start to improve, and it's all part of the developmental process. But when a child is first born, one of the key things that happens is that they're born with what are called primitive reflexes, and primitive reflexes occur at the spinal cord. So they're monosynaptic reflexes, and the first one is a sucking reflex. And a sucking reflex is basically when something is inserted into the mouth of a child, they start sucking. So this is obviously a reflex that's for survival, for breastfeeding. Then there's a rooting reflex, and the rooting reflex is if their cheek is stroked, they turn their head towards where the stimulus is, and that's also a reflex that's for survival to identify the nipple. So if they feel a breast, they can immediately move their head towards it. So the rooting and sucking reflex are really designed to help a child survive and be able to latch on to the nipple for breastfeeding. Then there's a grasp reflex, and a grasp reflex simply means when you grab the hand just starts to close down. And the grasp reflex also occurs on the feet, which is the palmar reflex where the toes curl up. And there's a startle reflex, so if you have a kid that's starting to fall, they'll become alert, and their arms will move, and their flexors and psoas will contract. And the startle reflex also, you'll see like loud noise jolt a child and have them cry. So it's also part of survival reflex. And then you have the tonic labyrinthine reflex, which is a primitive reflex, in where a child, when they turn their head, their extensors on that side turn on and the flexors on the opposite side turn on. That's to prevent them from falling over. So those primitive reflexes are intact as soon as the child is born, and then when a child is born, they're actually in a really high sympathetic tone. So, with newborns, the heart rate is anywhere from 70 to 190 beats per minute. Their pupils are very, very dilated. They're really in a actual fight or flight response. And part of the reason is because the spinal cord has a region called the intermediolateral cell column, which activates the sympathetic tone. And that pathway isn't dampened until the brain starts to develop. And as the brain starts to develop, there are projections from what are called hypothalamic spinal projections and activation of the parasympathetic nuclei 5, 7, 9, and 10 in the pontomedular areas of the brainstem. And then they start to support digestion, swallowing, and saliva production. But when the child is first born, though, they're really in a sympathetic survival, fight or flight response. The heart rate is up, and they're not digesting well, they're not swallowing well, they don't have very, very much saliva production. And these things start to change as the brain starts to develop. So as the brain starts to develop, and the cortex and different regions of the brain start to fire into the brainstem and spinal cord, some changes in these basic reflexes will start to take place. First of all, as the cortical spinal tract starts to develop and a child starts to walk and move, and usually around the six months to for sure by the second year of life, these cortical spinal tracts start to activate the anterior horn, and they have an inhibition response there. And these primitive reflexes, like the starting reflex, sucking reflex, gas reflex, tonic labyrinth reflex start to diminish, and they should resolve. With some children that have development delays, you'll see some of those reflexes persist. We'll talk about that during the physical examination, but that's just a part of normal neuroanatomical function. The other key feature that takes place when the brain and the cortex start to activate and respond, there's pathways in the hypothalamic regions, hypothalamic spinal regions. What they do is hypothalamic spinal tracts, they excite inhibition of the intermedial cell column. In other words, they decrease sympathetic tone. So as the brain starts to develop, their sympathetic tone goes down. So pain percepts, not as much pain in child development disorders, but increased heart rate. Heart rate starts to go down. The pupils start to get less dilated, and as the hypothalamic spinal pathways get activated in the parasympathetic system, and where you have cranial nerves 5, 7, 9, and 10. 9 and 10 get activated so they can swallow and they can start to digest their food. And then 7 and 9, cranial nerves, superior and inferior cellulatory nucleus activates for their saliva production. So as time goes on, as the first 6-9 months to 1 year happens, you can see children start to have their dilated pupils start to become smaller, the heart rate starts to go down, they can start to digest food and swallow and produce saliva. And those are all indications that these descending pathways from the brain are working. And also these primitive reflexes start to diminish as the brain starts to develop. So those are early pathways that are involved with neurodevelopment. Now, the other key things you really just want to make sure you understand before you go into the course is these pathways involving the vestibular complex. So within our inner ears, we have this vestibular complex, and we have canals. We have an anterior, horizontal, and posterior canal. Anterior canal senses motion this way. Horizontal canal motions rotation. Posterior canal recognizes motion back. And then we have in the vestibular complex otoliths, which pick up anterior translation, posterior translation, and then superior and inferior translation, like going up and down an elevator. But those pathways are actually intact right when a child is born. And those intact pathways activate projections into the cerebellum. And the cerebellum is one of the first areas that starts to really develop during childhood development. So one of the things you can see here is this diagram here. And the cerebellum, as you can see here, is going to project immediately into the brainstem. And as motion and movement take place, and a child that starts to move and rock, and parents hold the child, they start swinging him back and forth. Those activation of these vestibular complex receptors fire into the cerebellum, and they fire into the brainstem. And as the brainstem starts to develop, we start to get these changes where we activate the parasympathetic nuclei, and that's where digestion, blood flow, heart rate, and pupil size start to become impacted. And as the cortex starts to develop, we get that hypothalamic spinal pathways, and these brainstem autonomic regions start to change. And this is all part of normal autonomic function. So when you actually see a child that starts to be able to digest food and swallow and be able to handle solid food, that's really indications that this whole brainstem region is working really well. Now, the cerebellum is going to get input not only from the vestibular apparatus, but it's also going to get input primarily from muscle spindles. And when you look at the brain's main source of constant input, or only source of constant receptor activation, is from gravity stretch on muscle spindles. So within all our muscles, we have muscle spindle fibers, and these muscle spindle fibers are aligned with the alignment of our muscles, and they stretch, and gravity stretches them. And as these gravitational forces stretch these muscle spindle reflexes, we get proprioceptive input that goes through what are called spinocerebellar pathways from the spine to the cerebellum, hence the name spinocerebellar pathways, and they start also activating the cerebellum. And head movement and head motion go through vestibular nuclei in the brainstem and then project into the cerebellum. And the cerebellum becomes one of the first places that are activated, and gravity and head movements are really what's starting to churn on activation of the brain for neurodevelopment. And gravity is really critical because when astronauts go into space, one of the key things that they face is that they face significant neurodegeneration because they're not getting that constant stimulus that they get on Earth, which is gravity activating these muscle spindle pathways. So as the cerebellum starts to develop, the cerebellum activates different pathways within its structure, and in the midline area of the cerebellum, you have an area called the vestibulocerebellum that starts to integrate these inner ear receptors with pathways in the brain involved with balance and stability. The cerebellum activates the very midline structures of its structure called the spinocerebellum. Let me go back here. The spinocerebellum, and the spinocerebellum fires all the intrinsic muscles where a child can actually sit up and stand erect. And then the cerebellum actually fires the contralateral cortex and starts to actually fire motor movement areas, as you can see here. So the cerebellar projections from here fire into the cortex, and those are involved with starting to turn on the brain. And as a child is born, again, you can see the vestibular pathways are intact, muscle spindles are firing as the cerebellum starts to activate. That spinal cerebellum starts to activate, intrinsic spinal muscles start developing, they can finally stand up. The cerebellum starts to activate regions of the motor cortex and actually start to light up other regions of the brain. And these initial movements and these initial activations is really where you start to see a child go from a lying down supine position to crawling to then being able to sit up and then to walking. And as they go through these changes where they can stand erect and have resistance against gravitational pull, their brain starts to develop in other regions. So we go from initial vestibular input, a muscle spindle input, to then activating the cortex, and then we start to develop sensory regions of our brain, and then we start to develop intellect and cognitive areas of our brain. But it's this initial movement and motion that is so important. So here you can see the cerebellum, muscle spindle, vestibular input, they activate, fire into the thalamus, the relay center, which activates other regions of the cortex, and then other inputs like auditory pathways, visual pathways, proprioception pathways, taste and olfactory pathway all start to activate the thalamus, right? So those are the very first neurological pathways that are involved with neurodevelopment. So just as a review, and then I'll kind of go back and go through this again. So when a child is born, visual pathways, auditory pathways, and vestibular pathways are intact. These vestibular pathways are critical because they're going to start activating the other areas of the brain, so a child can start to develop the ability to sit and to stand up. And these pathways that activate through head position and movement start to fire into the spinal cord, and they start to activate the brain, and those pathways then activate the spinal cord. And that's where you start to see autonomic centers start to change, and over time, digestion and blood flow and heart pupil size start to change, and they go from more of a sympathetic dominance into starting to develop some parasympathetic functions. And these types of responses start to then turn on different regions of the brain. So those are the first pathways that are involved in neurodevelopment. So I wanted you to be familiar with what the cerebellum does in these vestibular pathways and how autonomics work and where primitive reflexes kick in. And then I just want to quickly review the different regions of the brain, just as a review. So the frontal lobe is the very front of the brain. The orbitofrontal is involved with executive functions, and prefrontal also with executive functions. That would be like planning, organizing, attention. This is an area that's commonly involved with attention deficit hyperactivity disorder, where they have issues with focus, attention, concentration. The frontal lobes are not developing very well. And then if you look at area number 12 here, this is the motor functional area. This is where motor planning takes place. So when you see kids with motor developmental disorders, and they have difficulty with initiating movement and planning movement, have like dyspraxia, we know that these areas of the brain are developing. Broca's speech area is the area of the brain that's involved with producing sound. So if you have a child that's having a hard time producing words, we know that this Broca's speech area is involved. And this is the motor function area that we have a somatotopic map of the whole body. And these are basically 3, 4, and 12 are all involved with activating muscle coordination, muscle movement, initiating and planning muscle movement. Part of the brain is involved with planning, organizing actions, and concentration and focus and intention. Then as we move further back on the brain, we have the parietal lobe. And the parietal lobe is involved with perception, proprioception, and sensations of like hot, cold, touch. And some kids that have sensory processing disorders where they can't feel things or they can't handle texture of things, like can't handle the texture of foods, or they're super sensitive, they can't handle the shirt on their back because of that increased sensory input. Those are letting us know that the parietal lobe may not be functioning so well. And as we get into areas like 5 and 11, this is the area of language centers, and these are the junctions where the temporal lobe, the parietal lobe, the occipital lobe start to integrate. These are involved with language centers of the brain. Dyslexics have issues in these language areas in the brain, in these areas. And then the temporal lobe is involved with auditory information and sensory processing of sounds. And so these are, the main structures of the brain. Then if you look at the internal parts of the brain, you can see number 6. This is the cingulate. This is part of the emotional brain, part of the limbic system. And you can see the corpus callosum here, thalamus, where you have the relay station, and then the cerebellum. And then over here you have the brainstem, where you have all the different types of autonomic functions. So those are the main structures of the brain, just to get you caught up with a basic review. Now, the other area that's really important in childhood developmental disorders is an area of the brain called the basal ganglia. And the basal ganglia is deep inside the brain. You can really see it best with the coronal cut. And here you see the cortex of the brain. This is the temporal lobe. This is the thalamus. And one of the things the basal ganglia does is it gates the thalamus. So remember, all inputs come into the thalamus, and the thalamus projects to other areas of the cortex. So the basal ganglia can excite or inhibit the thalamus, and it's really the inhibition part that we're really concerned with certain childhood developmental disorders. So when kids have hyperkinetic activity, like motor tics or vocal tics, then we know this basal ganglion direct pathway is not doing its job. Symptoms like OCD, obsessive compulsive disorders, we know that it involves the basal ganglia indirect pathway. So there's conditions like PANDAS, where there's antibodies that cross-react and injure these areas of the brain. And then there's also projections from the basal ganglia that are involved with impulsivity and hyperactivity in ADD kids. So that's the basal ganglia area. Excuse me. So in summary, as you go into the course, just understand that primitive reflexes start in the spinal cord. Children are born in a sympathetic tone first, and as they develop, the parasympathetic system starts to get activated. Over time, they have suppression of their primitive reflexes. The cerebellum is where vestibular input and muscle spindle come in, and that turns on activation throughout the rest of the brain. And then as the child starts to stand and move and function, that starts to build up pathways in the brain that then involve intellect and cognition. And then we talked about the different regions of the brain, and then the basal ganglia, which gates the thalamus. So those are the basic structures of the brain. I hope that this review helps you to recall and remember those things. And if you're not familiar with some of these regions, you may want to look them up. Now, the course that you'll be going through isn't going to be really, really deep, thorough neurology, but this is just the basic fundamentals you should know. If you know this information, you should have no problem with the rest. And we'll be reviewing these pathways on the course as well. And we're going to really emphasize more of a functional medicine approach and a diagnostic evaluation and clinical application approach. So it's not really all about neurology. But as you go into the material, it's important to just have some basic review of these structures, because we'll be going through them and naming them off for certain mechanisms. So thank you for watching this pre-conference video, and I hope this helps, and thank you for registering for the course.